Hi. Okay, my in-laws are still at the grocery store, so I'm gonna try to sneak in one more quick video before they come home. It would just be a little awkward for me to be doing chemistry videos with them sitting in the living room, you know. So we'll see how far we can get. Okay, so in our last video, we learned about energy diagrams, and we put an exothermic energy diagram into your notes. So now we're going to do an endothermic energy diagram. So I have it set up here. Remember, the y-axis is the energy in kilojoules, and the x-axis is the reaction coordinate, or in other words, how the reaction is progressing, or as it progresses. Okay, so for this one, let's say the reactants start down here. Okay, so we'll put reactants. And when we are talking about the energy of the reactants or the products, what I really mean is the sum. Remember this Latin letter here, sigma, means the sum of the heat of formations under standard conditions. So there is a table of those in your book that we used in one of our previous videos, probably 13C. And so where we're getting this energy for the reactants is adding up the different energies, the heat of formations for the different reactants that are involved, okay? So there's the reactants, and then of course it needs to be activated. So the reactants need to reach a certain energy, and this is the activation energy, would be the difference between where they started and where they need to be to get the energy going. So this is the activation energy. And then in an endothermic reaction, the products would end up having more energy than the reactants did at the beginning. So again, this is the sum of the individual heat of formations for each of the products that have been formed. And so this is an example of what an endothermic reaction would look like. I also wanted to add that you could find the delta H, or the change in enthalpy, for the whole reaction by comparing the energy of the reactants and the energy of the products. So the space in between here would tell you the delta H. And the way that you would do that to get the proper negative or positive number is, remember, to use Hess's law. I'll write that here. Use Hess's law to calculate delta H. Hess's law was delta H, and this little circle here means under standard conditions, so that's room temperature, which is considered to be 25 degrees Celsius, and the pressure would be 1.00 atmospheres. That's what the standard conditions means. So the delta H would be the sum of the delta H of formation for the products. So this number right here, you would start with the energy of the products minus the sum of the delta H of the reactants. Okay, let's take a look at example 13.5 in your book, and we will try to apply or read these graphs correctly and see if you can answer these questions. So example 13.5, the first question there says, A, which diagram represents the most exothermic reaction, and what is its delta H? So actually, I think I'm going to draw these different, just real quickly, sketch these onto my whiteboard here. And you can put them into your books as well, or into your notes. Okay, so in example 13.5, we have three different energy diagrams that we're going to be comparing. The first one looks something like this. I'm not going to write in the different X and Y values. We'll just kind of draw the shape. So the first one starts here, activation energy, then it drops pretty low like that. And then number 2 looks like this. The reactants start down here. Then we've got an activation energy, and then the products. And number 3 starts here, just a little increase for the activation energy, and then the products end up down here. Okay, then I can refer to those as we go through the questions. So 13.5a was looking for which is the most exothermic and what is its delta H. Okay, remember that in an exothermic reaction, the products have a lower energy than the reactants. So the two exothermic reactions, looking at these different graphs, would be reaction 1 and reaction 3. To find out which is the most exothermic, we actually have to figure out what delta H is. Okay, so delta H for Roman numeral number 1. Remember, we're going to take the energy of the products minus the energy of the reactants. So looking at number 1, the products end at 50 kilojoules and the reactants started at 100. So 50 minus 100 would be negative 50. So we'll just write it under here, delta H equals negative 50 kilojoules. And then for number 3, the products end at about 25 kilojoules. And the reactants were at 50, so we're going to do 25 minus 50. So this delta H would equal negative 25 kilojoules. So which is more exothermic? That's right, reaction number 1. So the most exothermic was Roman numeral number 1, and then the delta H for that was negative 50 kilojoules. Okay, so these are just some examples of how you would have to read these graphs and what kinds of questions you would have to answer from them. B, which diagram represents the reaction that is easiest to get started? Okay, so now we're going to be looking at the activation energies. So we're going to compare the energy of the reactants to the activation energy, and we want to know what's the easiest to start. So it's going to need the least amount of energy to get started. Okay, so in reaction number 1, we had to go from about 100 to about 125. I would say the activation energy is at about 125. So this is about 25 kilojoules. Activation energy, just abbreviate like that, is about 25 kilojoules. For number 2, we had to go from 20 kilojoules to about 55. So I'd say that's about 35 kilojoules for the activation energy. And then for number 3, to get started, we had to go from 50 kilojoules to about 55. So this one, we only needed a difference of about 5 kilojoules. So the easiest reaction to get started would be reaction number 3. 3 is easiest to activate. And then, lastly, C. Which diagram represents an endothermic reaction? Okay, so we'll write that an endothermic reaction, the products have higher energy than reactants. So the only one that was endothermic was reaction number 2. If the products end up with more energy than the reactants, it means that the products had to absorb energy from the surroundings and gain that energy and keep that energy, and therefore the surroundings, it's going to be cooler. So it's endothermic. So if you touched the vessel or the beaker that you were working on, it would be cooler. So this would be endothermic, number 2. Okay, so those are the types of questions that you have to answer with energy diagrams. And yay, I made it before my in-laws got home from the grocery store. I squeezed another video in. So in my next video, we will move on to the second law of thermodynamics.